Morning, everybody. Before we get going, did anybody have any questions about anything? All right, just a couple of announcements then. So what I'm going to do for your exam is I'm going to have it in two parts. So one of them will be kind of a traditional in-class part, if you will. Though it won't really be in class. It'll just be, there's a time frame that I want you to be able to do it in. And then the other part will be a take-home-ish part. So just to give you a little bit of a clarification on what I mean by those. So your in-class portion will be Friday. On Moodle, there is an assignment set to go that will open up at 8:45 a.m. on Friday morning. And you will need to complete it by 10:15 a.m., have it uploaded to Moodle by 10:15 a.m. So just, again, that's just to give you a little bit of time to make sure that you can get it downloaded, get everything settled, and then basically have class time to get it done, and then upload it into Moodle when you're done, so you have time to do that afterwards. You would upload it just much like what you've been doing with your homework. On that part, I would expect that you're going to be doing this on your honor. I'm not going to monitor you. I will be on Zoom if you have a question, so if you want to log into Zoom and have a question for me, that's perfectly fine. But I won't be monitoring you. You'll be on your honor, but I do expect that you will do this like you would do an exam for that portion. So no book, no notes, no checking the internet, no talking to people, those kinds of things. That particular part is more computational. So being able to do things like take a determinant, find an adjoint, check if something is linearly independent using your calculator, check if something spans using your calculator, those kinds of things. So that particular part I expect to be computational and, again, done on your own. So that's why that one has a time limit on it. The other part will be more of the take-home idea, a little bit more conceptual. It's set to open up, I believe I have it set to open up at Wednesday at noon, and it will be due by Friday by 5. So you'll have a couple of days to do that. And that'll be the more conceptual part. There will be some proofs that you'll have to do. That's where you'll have to prove if something, whether or not something's a vector space, prove if something is a subspace, maybe a couple of things to do with basis proofs, those kinds of things. So again, that will be the more conceptual part. I will send an email out with all of these details so you'll actually have it in writing so that you can see it in front of you, so that you don't have to try to copy all of this down while I'm talking about it or have to go back and rewatch the lecture to see what I said or didn't say. So I will send out an email detailing all of that either this evening or tomorrow morning so that you can see what's going on. I think I actually may have already have another email. No, that's something else. But I will have an email sent out for you for those purposes. But I just want to let you know that was coming. But again, the in-class part, there's not any proofs. There will be a few true-false on there, but there won't be any proofs at all on the quote-unquote in-class part. It's more the being able to do the computations and being able to do the interpretations from the computations that we've talked about. So any questions about that at all before we finish off section 5.4? All right. Well, then let's continue on with our discussion with basis. So on Friday, we left off with this notion of the plus-minus theorem. So this plus-minus theorem talks about having a non-empty set to start with. The first part was if the set you start with is linearly independent, and you have another vector that's not in the span, then if I add that to the previous set, if I stick V inside of S, it's still going to be linearly independent. Now again, just thinking about what the words linearly independent means, it means that it means that these vectors that are in S don't depend on one another, meaning that I cannot write one of the vectors as a linear combination of the others. That's the idea of being linearly dependent, right? So if it depends linearly, if the set is linearly dependent, then I can write one of the vectors as a combination of the other ones. That means that one of the vectors depends on the other vectors in the set. So if I have a vector that's not in the span, that means that I cannot write this vector, that v, as a linear combination of the vectors from S. In particular, the vector v does not depend on the vectors from S, right? So if I stick it inside of S, it's still going to have to be linearly independent. That's kind of the intuitive idea behind it. If it's not in the span, it doesn't depend on the other vectors. So if I throw it in the set still remains linearly independent. And the idea behind the proof is what we talked about right at the end of class last time. Our definition, our actual technical definition of linear independence is that you start with a linear combination that gives you the zero vector. Yes? Okay, well, I will repeat it. What was the last thing? What was the last thing you heard? Okay. When I started talking, okay, so going back up to the top here with the theorem. So if I have, oops. So again, thinking about what we mean by linearly independent, that means that none of the vectors depend on each other, right? I cannot write a vector in the set, any vector in the set, as a linear combination of the other ones. So if I know that I have a vector here, v, that's not in the span, then I know that v is also not a linear combination of anything in S, because remember, the span is the set of all linear combinations of the elements in S. So that means that if I throw v in the set too, it's still going to be linearly independent because I still cannot write any vector in this new set as a linear combination of the other ones in the set. So that's what I meant by intuitively. If I have something that's not a linear combination, then I can go ahead and throw it in the set and still be linearly independent because I still have a bunch of vectors that don't depend on each other. They're independent of one another. That's the idea. Did you hear that part, I hope? Okay, cool. Good. Sorry about that. Yep, you're welcome. Yeah, definitely stop me and make sure I repeat if you can't hear it. So, all right. So, again, going back to the rigorous definition of linear independence, we start with a linear combination that gives us the zero vector. These v1 onto vn are, I'm saying, the ones that are in S to start with, and v is the new one that I'm trying to add to the set. So I'm doing a linear combination of those n plus 1 vectors. I'm going to move this one to the other side. So if my k sub n plus 1 here is not 0, then I can divide both sides by it, meaning that v would be a linear combination of the v1 out to vn, but that's exactly what it means to be in the span of v1 out to vn. I would have v as a linear combination of the v sub i's, which we said didn't happen, right? So this part can't happen. So we must have that k sub n plus 1 was 0. Now if k sub n plus 1 is 0, then I have the 0 vector on the right-hand side. So I have a linear combination of the v sub i's that's equal to the 0 vector. And since we're assuming that the S, and I use the v1 onto vn to represent the set S, since we're assuming that S is linearly independent, if we have a linear combination that equals the 0 vector over here, then I had to have all the constants had to be 0. So going back up to this line here, we started with a linear combination that gave me the 0 vector, and we showed that all of the constants had to be 0. So that's exactly what it means to be linearly independent. Again, just thinking about it intuitively, that's not a huge surprise that if I have a set that's already linearly independent, and I have another vector that doesn't depend on any vector in that set, well, I can go ahead and throw it in there and it stays linearly independent. That's kind of the idea. It's not depending on the other ones. Any questions on that particular part? Okay, so let's go to the other side of the plus-minus theorem. This is part B here. And it says that if you have an element in S, if you have a vector in S that is a linear combination of other vectors, then you can throw it out and you didn't change the span. Okay, so let's see why that's true. All right, so I'm going to give us different letters than V's this time. So I don't have the V's and the V's of I's. So I will actually use different letters. So let's use S. So let's say S is a set of vectors W1 out to Wn, and we throw in the vector V. We're assuming that V is a linear combination of the other vectors. So let's say that V is equal to C1W1 plus C2W2 out to CNWN. Okay. So we want to show that the span of when I take S and throw out V, I get the same thing as the span of S. So what I mean by this is, certainly if I take the span of S minus V, I have to have a subset of the span of S, because remember, the span of S is the set of all linear combinations of vectors from S. Well, if I throw out V, I'm still going to have linear combinations of vectors in S. So anything that's in the span of S minus V is already in the span of S automatically. Because you could think about just using the 0, you could just think about eliminating this vector here, and then it's just doing the linear combinations of the W1 out to Wn. It's still, that would be something that's in the span of S minus V, but it's also still in the span of S because I'm using a linear combination of vectors from S. I can think about just using the 0 as the constant that I'm multiplying by the V. So again, I don't have, I certainly have containment one way. I certainly have the fact that the span of S minus V is contained in the span of S. So just to write it this way, certainly the span of S minus V is contained in the span of S, without a doubt. Okay, we certainly have containment that way. We want to show containment the other way. We want to show that if something's in the span of S, then it's also in the span of S minus V. So let's let X be an element of the span of S. Then to be in the span, oops, make that a vector. To be in the span, we know that this X has to be a linear combination of the vectors in S. So just to write that down, then there exists, I'm going to use different letters than the C's because the C's I'm using specifically for the linear combination that gives me the V. So I'll say there exists K1, K2, Kn, Kn plus 1. Okay, there exist constants K1 out to Kn plus 1 such that X is equal to K1 W1, K2 W2. That's a 2. It's an ugly looking 2. Kn Wn, and then I need to put this on the end. A Kn plus 1 V. Again, this is exactly what it means to be in the span. It is a linear combination of the other vectors. But what do we know about V here? Well, we have a linear combination of the W's that I can plug in for V, don't I? So we can take this linear combination and do some rearranging. I can put in the C1W1 out to C1Wn, put that in here, multiply it by the Kn plus 1, and then regroup like terms. So you'll get a K1 plus a Kn plus 1 C1 times W1. You'll get a K2 plus a Kn plus 1 C2 W2. And then you get a Kn plus Kn plus 1 Cn times Wn. And notice that we've eliminated the V totally. The reason why we were able to eliminate the V was because V actually depended on the W1 to Wn, which means that I don't need it to generate elements that are in the span. I only need the other elements that are in the set. So the conclusion here is therefore X is in the span of S minus V. So we prove containment the other way. So now we get the spans are actually equal. Yes. Sure. So what I did was I took this expression here that I'm underlining in red. I plugged it in for V here. Okay. So then I had to take this Kn plus 1 and distribute it through to each term. And then I collected like terms. So notice in the first one, you'll get a Kn plus 1 times the C1. Those will get multiplied together. And so that has a W1 on it. So does this one. So then I just factored out the W1. And I did that all the way across. That make sense? Cool. Other questions on this? All right, so what does this mean for our purposes? All right, so we've already talked about the idea of basis. And remember that basis has to be linearly independent and it has to span. Well, notice that if we have a linearly independent set, I can potentially add more things to it and keep it linearly independent as long as those things that I'm adding to it aren't in the span. So I can take a linearly independent set and I can keep building it up until it actually spans the whole vector space and make a basis out of it. On the flip side, if I have a spanning set for the vector space, I can reduce vectors out of it, or I can take vectors out of the set until I end up with a linearly independent one and make a basis. So what does this mean? There's a couple of things that this means. The first thing that it means is that any linearly independent set can be expanded to form a basis. if I start with a linearly independent set, I can throw vectors into it to make it into a basis. I have to be careful about how I do that, and we'll talk about some examples of how we do that here in a minute. But in general, if I start with a linearly independent set, I can add vectors to it until I get enough in there to span the vector space as well and make a basis. The second thing is that any spanning set can be reduced to form a basis. The third thing says that if I have a linearly independent subset, then the number of elements in S has to be less than or equal to the dimension of V. So remember that when I use the absolute value bars around a set, that notation means the number of elements that are actually in S. So just to say this another way, a basis for V is a maximal linearly independent set in V. A basis is as big as you can ever get and still be linearly independent. If I try to throw one more thing into it, it gets too big and can't be linearly independent anymore. And then on the flip side, if the span of S is equal to V, so if S is a spanning set, then then S has at least as many elements in it as the dimension. So said another way, a basis for V is a minimal spanning set. So again, a basis represents as big of a set as possible that can still be linearly independent, and it represents a spanning set that's as small as possible and still be a spanning set. So one of the things this tells you is that if you have a set that has the same size as the dimension of V, if it's linearly independent, it automatically is a basis. Or if it spans, it's automatically a basis. And that's actually Theorem 5.4.5 in your book. Okay. So just to write that down real quick. It says that if a set has the same size as the dimension of V, then S is a basis. If either S is linearly independent, or S spans V. And this isn't, if you think about how we've checked linearly independent and span, think about how we've checked these things. What do? We take the vectors, we put them in a matrix, and we row reduce. That's how we check if a set of vectors is linearly independent or if it spans, right? The first thing we do is we take the vectors, we put them in columns in a matrix, and we row reduce. For linearly independent, we need to see a pivot in every column. To be spanning, we need to see a pivot in every row. Well, the only way you can get both is if you have the reduced row echelon form to be the identity, right? if you don't see the identity matrix as your reduced row echelon form, you're either going to have a pivotless column or a pivotless row. It's the only thing that you can't have a pivot in every row and every column unless it's square and you see ones down the diagonal. It just doesn't happen. So that's all this theorem is saying, is that if you have a set of vectors that has the same size as the dimension of the vector space, think about it in terms of how we check it. If you're going to put it in a matrix, well, you started with a square matrix to start with, right? The number of elements in the, if you think about it just in terms of real vectors, right? Vectors from Rn, the number of vectors in the set are how many columns you're going to get. Because remember, we take each of the vectors and stick them in columns in the matrix. So this is telling you the number of columns that are going to be in your matrix. The dimension of the vector space is basically telling you how many rows you'll get in your matrix. So this statement here is telling you that you have a square matrix when you do that. And if you have a square matrix, the only way that you can get a pivot in every column and every row is if you have ones down the diagonal. So if you have one, then you have the other. That's the idea. All right. So let's see if we can put this stuff to work. So actually do some computational types of things. So let's look at this first example. I had typed in number 22 on page 264 and then realized, hey, I gave that to you as homework. So let's change it up and do a different one. This one says it wants us to expand the negative 2, 1, negative 2, 1, negative 1, negative 1, 2, and then the other vectors to form a basis for R5. Now, I know automatically that this cannot be a basis for R5. The reason for that is because, what is the dimension of R5? It has to be 5, right? The dimension of R5 is 5. So that tells us that there have to be 5 elements in a basis for R5. No matter what. Okay? There are only 3 in here. There are only 3 vectors in this particular set. So notice that since there are only 3 vectors in here, this set has no hope of spanning R5. It could be linearly independent, but it cannot span. Okay? So that's property number 4 right here, right? That I just wrote up. It's at the top of the screen. It says that if we have a spanning set, then it has to be at least as many vectors in the set as the dimension of the vector space. This one only has 3 elements in it, so it can't span. Okay. All right. So we want to add 2 more vectors to this set and end up with a basis for R5. That's the idea. I want to make sure I use these 3, but I want to add 2 more. Now, I don't want to guess at what they are. I want to be a little bit more algorithmic in my process. So the idea behind this is going to be the following. And this is going to end up basically using the plus-minus theorem idea. All right. So I'm going to put the first 3 vectors as columns of a matrix. And now I'm going to try to figure out what other vectors I can add to make it remain linearly independent, but also span. Well, I automatically know a set of vectors that already spans R5, and that's our standard basis. So in the next 5 columns, I'm going to put in the standard basis for R5. The reason I do this now is with these 8 columns, I'm guaranteed to have a spanning set because I already know that these span without a doubt. So what basically the whole process is that I have 3 vectors here that I want to put in my basis. I want to figure out which two of these extra ones I need to throw in to make a basis. Okay? So to do that now, we're going to row reduce. So let's see if I can do that. Let's see if I just share my screen. Try to leave this on the screen while I put it in the calculator so I don't have to ask you what the numbers are every single time. If I can get my calculator on the screen at the same time. I don't know why it doesn't like to do that. Doesn't like to put two things on the screen at the same time for some reason. I don't know why. There it is. It's hidden. Where are you hidden? Oh, for heaven's sake. There it is. Sorry. Operator error. On the screen and get the other one in front of it. Okay. Phew, that was hard work. Alright, so let's go to Matrix. Of course I did. Edit. I need a 5x8. And then I need to put in these other ones too. 4, -3. And I already have 4, -3 in there, so then I need to have 1 and then a bunch of zeros. Alright, and the next row is 1, -2, 1. And then I'll have 0, 1, 0, 0. Oh, hey, what's going on? Why did you do that? Where's my calculator? That was weird. My calculator disappeared on me, sorry. Alright, let me check my numbers again. 1, -2. No, that's why. Doesn't like that negative sign. -2. And 1. And then 0, 1, 0, 0, 0. Alright, and then the next row, -1, 3, 0. So -1, 3, 0, and then 0, 0, 1, 0, 0. And then -1, 2, -1. So -1, 2, -1, and then 0, 0, 0, 0, 0, 0, 1, 0. And then the last row is 2, -4, 2. So 2, -4, 2, and then 0, 0, 0, 0, 1. Phew, finally. Yes. Yes. It should be -2. Thank you. -2. Thank you for checking that. All right, cool. Appreciate that. Sorry about that. All right. So, now, to see which ones we need to add, we'll get out of here I want to do the reduced row echelon form, which is B there. And then I want to go back and grab matrix A. All right, so now if we look at the elements here, we notice that we get a pivot in column 1, we get a pivot in column 2, we get a pivot in column 3. So if I ignore the other 5 columns, I definitely see that we have a linearly independent set here, without a doubt. Okay, so now let's figure out which other ones we need to add in. Well, if I put this one in here, I'm not going to get a linearly independent set, because notice it depends on the other theory, right? In fact, it says that if I take 3 times the first one, plus 1 times the second one, plus -1 times the third one, I get this 4th column. I've written this one as a linear combination of the other 3, so I don't want to add this one in. This one, however, this column is a good column. It's not a linear combination of the other 3, so I want to add in this column. And then notice the same thing over here. I want to add in this column, but not the last one. All right? So when I'm going to expand to be a basis, I want to go back to my original matrix. I'm going to grab column 5 and column 7. Well, if I go back to the original matrix, column 5 was this one, and column 7 was this one. So you'll add, to make your new basis then, you're going to add this vector and this vector to the set that you started with to get your linearly independent set. So your basis then will be the -2, 1, -1, -1, 2. Your 4, -2, 4, -2, 3, 2, -4. That was weird. Oh, stop it. Your -3, 1, 0, -1, 2. And then you're going to add in 0, 1, 0, 0, 0. And you'll add in 0, 0, 0, 1, 0. Not the vectors that were in the reduced row echelon form, the ones that correspond back to the original matrix. So we had pivots in columns 1, 2, 3, 5, and 7. So those are the vectors that we use for our basis. Besides the technical issues I was having with the calculator, is that process okay? So again, the idea is to take the vectors in the basis that you want to in the set that you want to expand to be a basis, stick the standard basis on the end, and then row reduce to figure out which of those elements from the standard basis you need to pick out or to put into your original set to make your basis. All right, we're going to do the reverse process for the second part here. This one says find a subset that is a basis. Well, notice right away, I know that this automatically I know this is not a basis because there are 1, 2, 3, 4, 5 elements in this set. What's the dimension of P2? 3, right? Because it's n plus, if it's P sub n, the dimension is n plus 1. So this tells me that any basis has 3 elements in it. So this has too many. Now I don't automatically know that it spans, but I do automatically know that it's not linearly independent. Okay, it might span, and if it's telling me to reduce it to form a basis, it's gonna span. It's not gonna tell me to do this and then not have it span. But in general, I don't know automatically it spans just because it has 5 vectors in it. Okay? Just because the number of elements in it's bigger than a dimension doesn't guarantee me that it spans. It does guarantee me, though, that it's linearly dependent. It can't possibly be linearly independent. It has too many vectors in it. All right, but the process for making this to find out, or excuse me, to reduce it to a basis is exactly like what we just did in the previous problem. You're going to take these, and you're going to make a matrix. So I'll put 3. Remember, with polynomials, we just take off the coefficients and put those as the columns in the matrix. So 3, 1, negative 1, 2, 0, 3, 1, 3, negative 15, 0, 1, 2, negative, 0, negative 3, 9. And we'll row reduce it to whatever that happens to be. So, see if I can make a mess of this again like I did in the previous one. Go grab the calculator. Go back and edit my matrix. And that one was a 3 by 5, right? Okay, and here, let's see, we have 3, 2, 1, 0, 0. So go back over here. We had 3, 2, 1, 0, 0. The next row, 1, 0, 3, 1, negative 3. 1, 0, 3, 1, negative 3. And the last one, negative 1, 3, negative 15, 2, 9. Negative 1. Three, negative 15. Is it 2 and 9? Yes. Cool. 2, 9. All right. Okie dokie. Let's quit out of here. And then I've already put in reduced row echelon form of A in the previous line, so I'll just grab it. Okay, so now we see that we have pivots in columns 1, 2, and 4. So that tells me that in that original set, I want to go back and grab element or vector number 1, vector number 2, and vector number 4 to be my basis. So going back to the original, I don't remember what the other numbers were, by the way, but this is 1, 0, 0, 0, 1, 0, something, and then 0, 0, 1, and then something over here. These tell me that I want to go grab column 1, column 2, and column 4. So your basis will be 3 plus x minus x squared. Number 2 was 2 plus 3x squared. And number 4 was x plus 2x squared. Questions about that one or the previous one? It's a fairly straightforward process to do it, right? You're just putting. Notice that this is all going back to the idea of solving systems of linear equations, like we talked about at the beginning of the semester. It's just an idea of putting it in the matrix and row reducing. All right. Well, I added a couple more problems here just to remind us of how we do these. I don't think I'm going to switch back and forth to the calculator because it's been a pain, but just reminding us of what we mean by these things to make sure that you can look at homework ones. So this is number 9 on page 264. What I'll probably do is after we're done, I'll make a video later today and post the calculator steps for doing this so that I can finish off the problems. But I want to get them set up for you so that you can see what we're talking about. So remember, for coordinate vector, we've talked about this before, but for coordinate vector, remember we're looking for C1 times the first vector, C2 times the second vector, C3 times the third vector, to give us the vector that we're interested in. If this is our set S, then the notation for the coordinate vector with respect to S looks like that. We put parentheses around the vector, put a subscript of S, and those coordinates will be C1, C2, C3. So when you're finding the coordinate vector, your goal is to figure out what these constants have to be. But you've done this several times this semester. We're solving a system of equations. So to find this coordinate vector, you want to take your vectors to -1, 3, 1, 0, 0, 2, 2, 0. Augment the vector that you're interested in, the 3, 3, 3, and row reduce. Your solutions to this system, whatever you get for C1, C2, C3, those are your coordinates. So all we're doing is setting up a system of linear equations, like we've done a whole bunch of times in the past. When we set up that system of linear equations, that just means that we end up putting the vectors as columns in our matrix and row reduce and read off the solution, just like we've done probably 100 times this semester. You would do the exact same thing here for number 11. You would take each of these matrices, put them as columns. So say I do -1, 1, 0, 0, make it the first column. 1, 1, 0, 0, make it the second column. 0, 0, 1, 0, make it the third column. 0, 0, 0, 1, make it the fourth column. 2, 0, -1, 3, make it the last column that you augment. And again, row reduce and read off the answer. By the way, the order in which you put these in doesn't matter for the first one, but as soon as you pick an order for how you're entering these into your matrix for the first one, you have to follow the same order as you go across. So the way I did it was I went upper left, upper right, lower left, lower right. So I followed that same pattern all the way across. But you could have done lower, you could have gone from right to left if you wanted to, up, down, doesn't matter. But as soon as you pick the first one, you have to use the same order for the rest of them. Questions on that at all? All right. So what I think I'll do, I've got a few more questions in here. This one, this number 15, is just basically start doing the same kind of stuff that you talked about, what we talked about back in chapter 1. You set up your system of equations and you row reduce and write out your solutions in terms of the parameters. And then your basis are just, remember when we wrote something like an S times a first vector plus a T times a second vector? The vectors that we have in there would be your basis. So I'll post an example with a video for that so that you can see that later. Let's see if I can answer a couple of these questions that I put at the end just to kind of review in the last minute that I have here. All right, so this first question says, can a set of 6 vectors span P4? So basically I'm asking you a spanning set. Is it big enough? Is this enough vectors to take care of the span? Well, that's just asking you questions about dimensions. So what's the dimension of P4? 5 again, right? So is 6 vectors enough to span a dimension, or span a vector space of dimension 5? Is it big enough? Yes. Okay. So the answer is yes. Does it have to? Am I guaranteed that it'll span? No. Okay, good. Okay, it can, but it doesn't have to. Let's look at the second question. Can a set of 7 vectors be linearly independent? Well, what's the dimension of m sub 2, 3 here? That one's 6. So can a set of 7 vectors be linearly independent with dimension 6? No. Okay, so that one's a no. 6 is the biggest that a linearly independent set can have. All right, so let's look at this next question where it says, can a basis for R8 have 10 elements? Well, what is the dimension of R8? 8. So can a basis have 10 elements? No. So what's wrong? So remember, a basis has 2 characteristics to it. It either has to be linearly independent and it has to span. Which of those 2 is automatically violated by having 10? Which can it not be? Can it not be linearly independent, or can it not span? Good. Cannot be linearly independent. It's too big, right? Remember that the dimension is the maximal linearly independent set. It's as big as a linearly independent set can be. So if the dimension's 8, the biggest linearly independent set you can have is 8. So it cannot be linearly independent with 10 elements in it. All right, for these last ones, this one's a no. If you have a subspace of V, if it's linearly independent in W, it also has to be linearly independent in V. So for the same reason, I can't have a dimension of W being greater than the dimension of V, because you would have a linearly independent set of W that was too big to be a linearly independent subset of V. And then for the last one here real quick, I know the dimension of M43 is 12. So if I already have 9 elements and is linearly independent, how many more vectors do we have to add to make a basis? 3. Good. All right. So the whole point of asking those questions was just to kind of review the concepts that we talked about. So I'll post another video probably this afternoon, but definitely by tomorrow morning, that kind of goes through these types of conceptual questions again, because I know I went through those quickly because of the time. But I'll get that taken care of. So any questions at all before we stop? Are we good? Yeah. Yes. No, you do. I thought those website problems. You don't have to. I'm just putting those up there for extra practice so that you can get feedback on the practice. So you've got. I would probably not necessarily do all of them. I would just kind of scroll through, and if there's something that you have a question about, you can click on. I think there's help or answer or something along those lines that you can get answers for, or you can always ask me about. Hey, you send me a screenshot of it and say, I tried this problem. I didn't understand it. Can you explain it to me? I just did it for pure practice. That's what my intent was, to try to give you another way to get practice where you can kind of get feedback, hopefully a little bit more quickly than otherwise. Yep, you're welcome. Anything else?